This is a tutorial on creating the block diagram, the Simulink block diagram for the spring pendulum dynamic system. I'm using MATLAB version 2017A, although this tutorial is applicable to earlier versions or later versions, as the fundamentals really don't change. We'll create the Simulink diagram. It's important to note that we never put numbers in a Simulink block diagram unless those numbers are part of the actual differential equations. The reason for this is that numbers represent parameter values, and parameter values may change. And if we have a parameter value in several locations, in order to change it, you would have to go into the block diagram and change that value at the various locations. If you leave the parameter as a variable, you only need to change it in the MATLAB workspace. That's where Simulink goes to obtain values of parameters that it doesn't know, so it can run the simulation. So we begin by opening up MATLAB, and you see that I have that in front of you. And I'll just go through step by step how we would create this block diagram. Normally, it's very important that you create this block diagram on paper first, so you get an idea of the scope and complexity of the block diagram, what blocks need to be used, how they need to be interconnected. That way, when you create the block diagram in Simulink, it will look professional and organized and easily understood by anyone else. I've done this often enough that I have a pretty good idea of the layout of the block diagram, and so I won't refer to anything written on paper. So the first thing we do is we open up Simulink. So I'll just go up here and I'll double click on Simulink. Simulink, you see, is initializing. In this version, you get some options. I'm just going to create a blank model, so I'll just click on that. And so it's creating the model. So now this is my workspace for creating my block diagram. I'm just going to move this over here in the center. I'll resize it a little bit, make it a little bit larger. And now what I want to do is I want to right now I'm just going to paste the well, actually it's not pasting the equations, the nonlinear ordinary differential equations, but you have those in front of you, so you can refer to these as we go. So I have the Simulink blank diagram workspace open in front of me. I'm going to open up the library here, so I'll just double click on that, and you see the library is over here to the side. Now the first thing I want to do is I want to drag into the workspace the blocks that I will need. So let me just go down the library here and show you where these blocks are coming from. First of all, in the continuous library, we will need an integrator, so I'll left click on that and just drag and drop. And you'll see that will appear there. I'll X out of this, gives me some information on some shortcuts. There's lots of shortcuts in Simulink. I'm not aware of many of them. You'll discover ones on your own. You'll discover a procedure that fits your style. There are some fundamentals you need to follow, but you'll become very proficient with this. As I look at these other blocks, we have PID controllers, transfer functions, transport delays, and I don't need any of those. If I go to discontinuities, I don't see anything that I need here. Saturation, hit crossing, friction, discrete, logic and bit operations, lookup tables. Math operations, I need several blocks. What I will need is a gain block. I'll drag and drop that over here. I will need a multiplication block, a product block. I'll scroll down a little bit. I'll need a, let's see, a summing block. I'll need a trigonometric block. And I think, I'll need also a, let's see where that is. Let's see, it's a math function block. So I'll drag the math function block in. I believe I have all of the blocks that I need from the math operations, model verification, model-wide utilities, ports and subsystems. If I go to sinks, I'll need a scope, and I'll need a 2 workspace block. I also could use an XY graph, may or may not need to use that, and that's all I need from that. In terms of sources, I'll need a constant block because I have constants in my equation, different nonlinear differential equations. I think we have everything that we need, and so now I can X out of the library. So once, the reason for drawing the block diagram before you get into Simulink is you know the blocks that you'll need, you drag them in. What I'll do now is I'll just resize these blocks to make them a little bit larger so they're a little more manageable. And this is my own preference, and it'll be easier for you to see. So I'm just resizing the blocks by grabbing the corner and resizing it. This is a summing block. If I double click on this with my left mouse, I'll see the icon shape can either be round or square. I always prefer rectangular. I'll hit OK, and it's just my own preference. So now that I've resized these, what I'll do is I'll simply grab all of these together, and I'll go up here to Display. No, actually, I'll go to Diagram, Format, Font, and I'll make the font larger. I'll make it 16 font. So now I can actually read these blocks and move them around. So I'm going to just bring these blocks down to the bottom of my diagram. And so we know the steps in creating this block diagram is that first in the equations of motion you solve for the highest derivative. And we've already done that. And then you create the stems. In this case, we create 2 stems. So the first stem I'll call the R stem. So I have an integrator. If I right-click, if I left-click on, excuse me, if I right-click on that and move away, it will replicate that. So I need 2 integrators there. If I right-click again and bring an integrator down below, I right-click again and bring another one over here, you see I've created my 2 stems, one for R and one for theta. So here I have, if I connect these 2, and I can do it automatically just by highlighting that line. And here, if I just bring the arrow close to the output of the block, you see the crosshairs, left click, move away, connect to that block. So I have these 2 stems. Let me position these a little more centrally located. So these are my 2 stems. You can annotate your block diagram just by double-clicking anywhere in the white space and typing. So if I just annotate here, I'm going to pick an Arial font, but I'm going to make it 16 so I can read it. And we'll say this is R underscore, or maybe we'll make this theta underscore double dot. So that's my theta double dot, and that'll be that line there. Then if I come over here and do the same thing, I can say this is theta underscore dot, and that will be represented by this arrow. And then over here I can just say, with a font of 16, I can just say theta. So I have theta, theta double dot, and theta dot. I can come down here and do the same thing. So I have, this is R underscore double dot, and over here I can type in R underscore dot, and then over here with a font of 16, I'll type in R. So these are now my stems, and I have these located under each other. You can see MATLAB helps me to organize this and line everything up. Once I've created the two stems, then I simply do what the equations tell me to do. So the first equation, let's do the R double dot equation first. The R double dot equation is the sum of 4 terms. So I'll take my summing junction, which is right here, and I'll just bring it up here to this location. I have 4 inputs. 2 of the inputs are minus, 2 of the inputs are plus. So if I double click on this and I just type in the signs, minus, minus, plus, plus, you'll see that I'll get those inputs. I'm going to make this a little bit larger. So, and then I'll simply connect these two together. So this says R double dot equals the sum of 4 inputs. One input is minus K over M times R. So here I have a gain block. So I'm going to put this gain block here, and I'm going to reverse it. So if I right click, I'll see rotate and flip. So I'll flip the block so it's going the other way. I'm going to make this block a little bit larger, and in this block I'm going to put the parameters K divided by M. K and M are parameters. I'll have to assign values to these later on. Right now I just input them as variables and I hit OK. This line here is R, so I'm just going to take this. I left click and bring it around. I can stop to redirect it, and I can grab this line and put it anywhere I want. So this says that R, which is this line, times K over M, is the output of this block. So I have minus K over M, so I have K over M times R, and that's going to come over here, and I'm going to route this into the first minus block. I'll move the arrow, the line, accordingly. Then I have a minus FT over M, which is a constant. So I have a constant block, which I'll put over here, and I'll put, double click on that, FT slash M. Now this is just a constant, and then I'll just connect this to the second minus input and reposition it. Notice that each block has a name. You can rename the blocks. For example, you could call this integrator theta double dot, integrator theta dot. The reason they have to have unique names is because when there's an error, MATLAB will refer to the block by name. You can hide the names, you can show the names, you can change the names, but each block has to have a name. So you can get as, again, as professional or as individual as you wish when creating these block diagrams. Just going to make this workspace a little bit larger. Just bring this down a little bit, give myself a little more room. Move these blocks down to the bottom a little bit. So I have two of my terms. Then I have a cosine theta times G. So this is theta. I have a trigonometric block, which I'll bring up here. If I double click on that, you can see I have a choice of functions. It's the sine. And this will look for the sine of the value of theta in radians. So again, MatLab Simulink does not keep track of units. So here we're using SI units. Theta is in radians. Theta dot radians per second. Theta double dot radians per second squared. So here if I just connect these two, this is theta. I take the sine of theta, and I want to multiply that by G. So I need another gain block, so I'm just going to right-click on this, grab this and bring this over here. I'll right-click on that, and I will flip that block. I'll double-click on that, and I'll change the value to G. So this then is supposed to be G cosine theta. So I have to go back in here and change this from sine. I'll change this to cosine. You'll notice in all of the blocks there are other choices that you may need to make at some point. There's always a help button that you can pick to inform you about the block. Right now I'm just making the changes that are necessary for the simulation. You can investigate all of this on your own. If you can do this, you can create a block diagram for Boeing 747. It's all the same, whether you have 2 stems or 200 stems, and whether they're all interconnected, interdependent, the procedure is the same. So we'll hit OK. So I have a cosine. So then this is the output. This is the cosine of theta, which I'm going to multiply by g. And then that's going to come around as a plus. So I'm just going to, I'll route this around the top like this. And I'll bring it in as a plus. You can move the line to be wherever you want it to be. So I have a g cosine theta. So now I have, you can see that this is minus k over m times r. This is minus ft over m. This is plus g times the cosine of theta. And the last is L plus R theta dot squared. So L is a constant, so I'm going to right click on ft over m and bring it over here. I'll double click on that and I'll say this is, we'll say this is capital L, and that's the unstretched length of the spring. I need to add R to that, so I'm going to just right click on the summation block and bring it over. I'll double click on it and I just need 2 pluses, so I'll go plus plus. So I have L going into it. I'll make this a little bit smaller. It doesn't have to be so big. And then R is what goes into the second summation. The way we pick off a value from a line is I go and I right click on the line. I left click on the line. No, let's see if I can remember. I go to the line, right click, and move away. And then you can see there's a node that appears. And so right click on the line and move away. And a node appears, which means that you see that I'm picking off that value of R. If lines cross and there's no node, then the lines are not interconnected. If a node appears, then the lines are connected. Note that if you print this diagram out, the nodes, which are very small dots on the screen, may not appear very clearly on the printed version of your block diagram. You may need to fill those in by hand because without doing that, the diagram will be unreadable, illegible. So note that only with a node are you actually picking off a value from the line. So the output of this then is L plus R, and you can see I can move this around. And then I want to multiply that by theta dot squared. So I need a product block here, so I'm going to take this product block, which multiplies 2 things together. Then I need theta dot squared. So I take a math function block, and I'm going to put that right here. And I need to make this into a square. So you can see all the options. So I get a square. It's going to square whatever the input is. This is theta dot. So I right click on that and I move away. So I bring that into theta dot. So theta dot into the square block gives me theta dot squared. Theta dot squared times the sum of L plus R. So I bring this into here. And that's a plus sign. And so then this comes around, and I bring this over here to my summing junction. So now I've created one of the 2 nonlinear ordinary differential equations. How do I know that I did this correctly? Very simply, write the equation from the diagram. So the equation from the diagram says R double dot integrated once is R dot, integrated once is R. R double dot equals the sum of minus K over M times R minus Ft over M plus G times the cosine of theta plus the product of theta dot squared times L plus R, and that goes into the summing junction with a plus. So that equation is correct. Now, as we're looking at these integrator blocks, you can't integrate without an initial condition. So the integrator block for R double dot will be an initial condition on R dot. Since we will start our simulation by giving it an initial displacement and not an initial velocity, the initial condition on velocity here will be 0, so I'll leave that as 0. When I go from R dot to R, I need an initial condition on R, so I'm just going to call this will be R underscore 0. So that will be my initial condition on R, and that's how I tell the integrator block what the initial condition is, and I'll have to define that in the MATLAB workspace. So I'll hit OK. So now the initial conditions for those integrators is defined, and now I'm ready to go and create the second diagram. So my second diagram is up here at the top, and now I need to populate that. I'm going to let's see, move these over to the side. I'm going to capture all of this, slide it down a bit so I can work at the top. So now I have my theta-stem, and theta double dot equals the sum of two blocks divided by L plus R. So I have a summing junction here. I'll right-click and put that here. And I have two minus signs. So this will be minus, minus. And I'll hit OK. And then I'll connect this to theta double dot. And it's a G, and it says that the sum of those blocks times 1 over L plus R. So let me move this summing block over here. And actually between that, I want to put 1 over L plus R. So I need a product block. I'll right-click and drag this product block over here. So I'll have this goes into that. And then I need a L plus R, 1 over L plus R. So this arrow right here is L plus R. And if I take this math function and right-click and put it here, and I double-click and ask for it to be reciprocal, so there's the reciprocal, and hit OK. And then I take this L plus R arrow, right-click, and bring it into that. The output of this is 1 over L plus R. And this I will then bring up here like this, and then I'll bring it over here to this, and you can then move the arrow to wherever you want. And so now I see that this product block is the product of the sum times 1 over L plus R. And then I can connect these blocks together, and that's what theta double dot is. So now I just need to create the summing junction, and the summing junction has minus G sine theta minus 2 R dot theta dot. So I already have theta here, so I'm going to right-click on the cosine block, and what I'll do is I'll right-click and I'll flip it. So I flip the block, and I'll just move it over here. So this is theta. I'll right-click, I'll bring it into the cosine block, so I have cosine theta, and I want to multiply that by sine, so I'll right-click on the cosine block, and I'll bring it over here. I'll right-click on it, and I'll flip the block. I'll double-click and make it a sine. Hit OK. No, I don't need to do that. I've already done that, so let me delete that, my mistake. I have a cosine block. Let me double-click on this, and we'll make this into a sine block. And hit OK. So I have the sine of theta. I need to multiply that by G. So I have G here, so I'll right-click, bring it over here. Right-click, I'll flip that block, so I'll flip it, and then I'll connect it. So now I have G sine theta, and that goes into this block with the minus sign that I see. Then I need 2 times R dot theta dot. So I have a product block, which I'll right-click and bring over here, and then I need to multiply that product block by 2. So I'll just grab a gain block someplace, and I'll put it right here. I'll double-click and I'll make that a 2. So I have the 2 times this product, and then I'll be connected. And then I need to multiply R dot by theta dot. So here is R dot. That's right here. Right click, and I'll bring it over and put it into that port. And then I'll just position it so it's a little neater. And then I have theta dot, which is right here. And I'll right click and I'll come away with that. And I'll put it into the second block. And so you can see there's theta dot. So I have 2 times R dot theta dot, and that comes in with a minus sign. So now I've created the second differential equation. Let me just move these blocks down here. The second differential equation. And I'll read what that is. It says that theta double dot equals the product of this arrow here, which is 1 over L plus R, times the product of, so that's 1 over L plus R, times the sum of what? Minus G times the sine of theta, minus 2 times the product of theta dot and R dot. So there's my block diagram. It's a graphical representation of my 2 equations of motion. And so now I need to then see how I'm going to have my outputs. I have a scope, so I'll just bring this scope over here, and I want to look at R, so I'll right click and bring the scope. So I'll just rename this, and I'll say scope space R. I'll right click on that and bring it up over here, and I'll rename this. I'll say this is going to be scope theta, and I'll right click on the theta line and bring it into scope theta. So now I can look as the simulation is progressing. The output will be shown on my 2 scopes, scope theta, scope R. I can also send the output to the workspace. So I'm going to just take this block over here, put it here, and say to workspace. And what I'll say is to workspace, and I'll say this is theta to workspace. And then I'll rename this, and I'll call this theta. And the same thing, I'll right click down here, and I'll say to workspace, but this will be, I'll name this R, and then I'll rename this R. So this is to the workspace, the value of R, and I'll connect it to my value of R right here. Okay, so now, and the theta then needs to get connected to my workspace, so I'll right click on theta and connect it to workspace block. Now the scopes and the 2 workspace blocks need to be configured properly. So look at the theta block, and it says here that save format, you must change this to array. The default is time series, but it must be changed to array. The same thing for the other workspace block. Change it to array and hit OK. Now the scope block, here's scope theta. If I double click on that, a window will appear. Now if I go up here to File, I can have more than 1 input. I only need 1 input, but if I go over here to Tools, View, Simulation, Help, you'll see all the choices. Now what we will do is this will show all of the data as the simulation progresses, and we don't need to make any changes here on either scope block. The XY graph we'll just delete, as that's sort of an extra. You saw that in the slides. It would just give you a plot of X of R versus theta. But here we want to see R versus time and theta versus time. So there's my block diagram. You can double click any place and you can annotate it, and this is the spring, pendulum, dynamic spring pendulum dynamic system, and you can put your name and date it and have this for future needs. Now, this will not run as you haven't identified the parameter values. So let's save this. We'll say File, Save As, and you can save it in a particular directory. And I'll save it here in, let's go to the directory for mechanical vibrations. So let's see, we'll go to Hofstra University, and I'll go down to mechanical vibrations, course, and we'll just say spring pendulum spring pendulum block diagram. And it saves it as a Simulink model, so we'll hit save. And you'll see it's not a valid model name, and the reason is because MATLAB does not tolerate spaces between words and file names or in variables. You must always use the underscore. Now it will save it accordingly. So it's called Spring Pendulum Block Diagram, and I save it in the appropriate directory. Now I still can't run this because it doesn't know what all these parameters are. It doesn't know what FT is, M, doesn't know what L is, doesn't know what K is, G, so I have to tell it. The easiest way to do that is to go back to the workspace and go up here to New Script. So I'll type, so now you see an editor appears. Now this is just like a normal Word editor. You can type anything you want. And comments are prefaced with a percent sign, in which case this is not read in the running of the program. So I'll say this is the spring pendulum dynamic system parameters, and I'll put another comment here. I'll say SI units, and now I can identify my parameters. So M is the mass that's attached. It's 1.815. I put a semicolon there because as I run this, I don't want it to repeat the value. I just want it to know the value. The semicolon suppresses the printing out or repeating of the value. L is equal to 0.333. Whoops. Let's do that on the next line. L is equal to 0.333, semicolon. G is equal to 9.81, semicolon. K is equal to, MATLAB is case sensitive, so please take note of that. 172.8, semicolon. FT is equal to 5.71, semicolon. And I believe those are the only parameters that we have in our simulation. Now, next to each of these, you could put a comment and say mass of attachment. Down here, you could write this. Whoops. Let's go back. And we can say here this is unstretched spring length. Down here I can say spring constant. And down here I can say this is spring pre-tension. You could list the units. In other words, you can go up here and say this is in kilograms, this is in meters, spring constant is newtons per meter, spring pre-tension is in newtons. So you can identify what these values are. We need to identify G, which is 9.81, semicolon, and you can say this is gravitational constant, and that's in meters per second, and we use the notation for squared, so it's meters / second squared. So it's a good idea to tell what the parameter is, give its units, even though we specified SI units. And so now I have in this Word document or this M file something that I can edit at any time. I need to save this, so I'm going to go over here and I'm going to save my M file. It'll ask for a name, so I'm going to say spring underscore pendulum spring pendulum parameters, and this will be saved as a MATLAB file, what we call an M file or a script file. I don't believe I need any parameter values, but if I do, Simulink will tell me when it can't run, so I can X out of this. Now, those parameters are now not in my workspace, so what you have to do is then you can open, right? You can open your spring pendulum parameter file, and you can run this. So if I go over here to run, I'll run that. And you can see over here in the workspace it says spring pendulum parameters. If I type who, you'll see those parameter values. And these are the values, and if I type, for example, FT, it'll tell me what the value is. So the values are now in the workspace, and so now I know Simulink can run I can run the Simulink program because it'll go to the workspace and get the value of these parameters. Let me go back to the block diagram. So let's make sure we've identified all the parameters. I've identified G. I've identified, let's see, FT and M, K and M and L. So all the parameter values have been identified. Oh, but I didn't identify the initial condition. So for example, for theta dot, initial condition is 0. For theta, the initial condition should be theta underscore 0. For R dot, the initial condition is 0. For R, the initial condition is R underscore 0. So let's go back to our editor and let's add those initial conditions. So theta underscore 0 is equal to, and we use the value of 0.021. That's in radians, so I can comment on that, and this is my theta initial condition, and that's in radians. Then I can say R underscore 0 is equal to, the initial condition we use is 0.115, semicolon, and I can say this is my R initial condition, and that's in meters. All right, so now I can go up here and I can save this, and now I can run it again. In which case, if I type who, you'll see I have those additional initial conditions. If I go back to my block diagram, everything now should be ready to run. And so if I go up here now to simulation, model configuration parameters, I want to run this with a start time of 0, and I want to run this for 60 seconds. I always want to use a fixed step, unless there's some reason why I should use a variable step. This way I have output at fixed increments, and I can use that very easily to compare to other plots. As I know how many data points I have. For the fixed step size, I don't want to make automatic. I make it 1 millisecond, unless for some reason I need to make it smaller for some numerical reasons. MATLAB has guidelines on this. I start with 1 millisecond. I use ODE5, a very standard numerical integration algorithm, and other than that, that's all I need to choose. If I go to data import export, everything has been already set up. So I don't need to make any other changes here. In the future, when we do real-time control, well, we can take our block diagram, and if it represents a control system, then we can auto-code generate the code into C code and download it to a microcontroller in a matter of seconds. All that, as you see here, code generation. So I can hit OK. So with that, I can now run my simulation. So if I just go over here to run, you'll see it'll compile and it'll start to run. And if I look at my theta and I look at my R, two scopes, I'm going to minimize this and we'll look at these two scopes. You'll see this is exactly what we see in the notes. This is the theta scope and this is the R scope. And you can see those plots. And now you can just verify that these plots are correct, and they are. If I go, I'll just close these. If I go over here to my workspace, and if I type who again, I'll see that I have the values of those parameters. If I type whos, it'll tell me what the size of these are. Now, I know there are many auxiliary windows that you can open, that you can find all of this information. My personal preference is I operate with one window open. So if I go up here to layout, I just show the workspace. That's all I have. I don't show the other windows such as command history or any of the other windows that are possible. So now if I want to, for example, I can plot t, comma, I can plot theta. And then if I want to plot on top of that R, you can see they have the same number of values. So I can plot t and theta, and then I can say comma, and then I want to plot t, comma, R. So I get two plots on this. There'll be two different colors. So I can say plot. Oh, and t is not a variable. T out is the variable. So if I just use an up arrow, I can see that again. So I'll just make the correction. It's t out, not t. T out is given automatically. And if I see that, you'll see my two plots. I can come in here and I can label this using the tools up here, or I can just type X label and then parentheses, single quotation mark, and say time in seconds. And I can type Y label and I can say this is R in meters and theta, and that's in radians. And then I can type in title and do the same thing, say spring pendulum predicted performance. And then if I go and look at my plot, you'll see that it has time in seconds, R in meters, and theta in radians, spring pendulum predicted performance. You could add a legend here, and you can see that if I go back to my scopes, I'll see that the theta scope is this waveform and the R scope is the other waveform. So I label these properly. So here I can label this is my, the red is my R value and the blue is my theta value. So now you can see what the colors represent, and I can move this around any place. So now this has the same information as the scopes. However, it is now more presentable for reports and you can annotate it in any which way you want. And you can save this plot. You can say File, Save As, and you can save it as a MatLab plot, and I can say Spring Pendulum Results. And it'll save as a MatLab figure, which you can then open up. So you can see that the creation of a block diagram is quite straightforward. The more you do this, the more you'll learn. You'll see that in the case study that I asked you to study, which is the half-cylinder dynamic system investigation, I create some Simulink block diagrams to solve those nonlinear equation of motion, and to also determine what the friction force and normal forces are for that system. So you can look at that and, again, create those block diagrams from scratch on your own. Only by practicing and doing it from scratch on your own without viewing this tutorial will you actually uncover things you don't understand and become expert in this, which you need to be. So this completes this tutorial. Please ask any questions that you want. Contact me by email or by cell phone, or ask them in class. Again, Simulink, MatLab and Simulink is a tool along with LabVIEW for practicing engineers worldwide. The more proficient you are in MatLab and Simulink, the more desirable you will be in industry, the more capable you will be as an engineer for modeling, for simulation, for control design, and for innovation. Thank you very much.